So first, let me introduce the next speaker. Today, Dr. Pierre-Yves Woudier will give us a tutorial on intrinsically motivated goal exploration algorithms for open-ended learning of skill repertoires. Okay, Dr. Pierre-Yves Woudier is a research director at INRIA and head of the INRIA and ESTA Parasite.
Okay, thank you very much. Do you see my slides?
Yes, and before he was a permanent researcher in Sony Computer Science Laboratory for 8 years. He studied theoretical computer science at École Normale Supérieure in Lyon. He received his PhD degrees in artificial intelligence from the University of Paris 6, France. He has been studying lifelong autonomous learning and the self-organization of behavior, cognitive, and cultural structures at the frontiers of artificial intelligence, machine learning, cognitive science, and educational technologies. He has been developing models of intrinsically motivated learning, pioneering curiosity-driven learning algorithms, working in real-world robots, and developed the theoretical frameworks to understand machines and humans to discover, invent, learn, and evolve communication systems. He has published 2 books, more than 100 papers in international journals and conferences, holds 8 patents, gave several invited keynote lectures in international conferences, and received several prizes for his work in developmental robotics and origins of language. In particular, he is laureate of the INRI National Academy of Science Young Researcher Prize in Computer Sciences and of an European Research Council Starting Ground, Explorers. He is also editor of IEEE Computational Intelligence Society newsletter on cognitive and developmental systems, where he organized the interdisciplinary dialogues in cognitive science, AI, and robotics, as well as an associate editor of IEEE Transactions on cognitive and developmental systems and frontiers in neurorobotics. He has been chair of IEEE Computational Intelligence Society Technical Committee on Cognitive and Developmental Systems in 2015 to 2016. He is also working actively for the diffusion of science towards the general public through the writing of popular science articles and participation in radio and TV programs, as well as science exhibitions. So Dr. Pierre-Yves, now the floor is yours.
Thank you very much. Thank you very much also for inviting me for this presentation today, the organizers. So today I'm going to introduce aspects of research on what with my team we've been calling autotellic agents, which mean agents that set their own goals and learn about the world by pursuing those goals that they set for themselves. And within an algorithmic framework that is relatively general and that we've been calling intrinsically motivated goal exploration processes. But before going into the details of this, I would like just to mention and thank many of my collaborators with whom I have been developing many of the works I will present today. So one extraordinary property of child development is that they spend a lot of time spontaneously exploring their environment. And they are not doing it because they are externally imposed some tasks. Rather, they are doing it because they are driven by different forms of what psychologists call intrinsic motivation, or what we may call curiosity in everyday language. And so during exploratory play, for example, they invent and they pursue their own problems. And such intrinsically motivated exploration has been argued to be key for children for several things, ranging from solving problems with rare rewards, but also to learn efficiently world models and to discover open-ended repertoires of skills. And so a number of teams in the world, including mine, have been working now for a while on modeling these capabilities, and also especially studying how they can be transferred into artificial intelligence systems and robots in particular. And so in this talk, I will review some lines of research in this direction, which I think are quite important for the future of AI. So first of all, there are different forms of intrinsically motivated exploration systems, different kinds of experiments that children can imagine and choose to pursue when they are in a curiosity-driven exploration mode. So a first category, which we've been calling knowledge-based intrinsic motivation systems, relies on generating intrinsic rewards upon visiting some states S of t, or experiencing transition from S of t, A of t to S of t plus 1. And such intrinsic rewards include, for example, prediction errors, uncertainty, or information gain. So this can be seen as enabling an agent to choose to make prediction experiments, and this has often been made on short time scales in the literature. So here it's important to realize that there is no notion of goals, as opposed to another form I'm going to speak about in a minute. And so this family of intrinsic motivation systems is used quite often for solving external problems with rare reward, or also for efficient learning of world models when the goal is to do it in a sample efficient manner. But then a second important category, which we've been calling competence-based intrinsic motivation, consists in systems where the agent imagines goals he would like to reach in the future. So here the intrinsic reward is actually replaced by a measure of interestingness that's applied to the self-generated goals, such as, for example, a measure of competence progress to reach those self-generated goals, and that is used to select which goal to pursue, which goal to sample and in what order. And so basically the agent decides which goal achievement experiment to make, and this has typically been studied over longer time scales in the literature, so longer time scale as opposed to knowledge-based intrinsic motivation systems. And so also this form of intrinsic motivation is used primarily to discover diverse repertoires of skills. And here when I say skills, I'm speaking really about parameterized problems, parameterized goals. And so in the talk today, I will really focus on this second family of systems. And this family of systems is also what we call autotellic agents. So there is a general framework that we've been working on to approach modeling this form of intrinsic motivation, and we've been calling this framework intrinsically motivated goal exploration processes. And it basically refers to all algorithms that have in common the following loop. So the basic loop is first observe the context, sample a goal internally, roll out the corresponding goal condition policy by using the current internal models, then observe the outcomes and update the various internal models for the next time the loop is going to be unrolled. I will come back into a little bit more detail on this loop later on. And so algorithms in this family differ along many dimensions. So for example, some are based on population-based techniques, which means basically that there is an explicit memory of policies associated outcomes that is stored in the agent. And examples of such systems are SAG area C or various quality diversity algorithms. But other IMJEP systems rely on goal condition reinforcement learning techniques, such as, for example, RIG or GoalGAN. You also have some systems that use learned goal embeddings, such as RIG, but others use hand-defined goal embeddings, like the system Curious. I'm going to quickly talk about those two systems. Some use learned goal achievement functions, such as the Imagine system. Others use predefined ones, like the L2 function in the embedding space in RIG. And some use goal sampling policies that are based on things like novelty search, like, for example, the skew fit algorithm, but also use other forms of goal sampling policies, for example, leveraging learning progress, like the Curious architecture. So concretely, how does this autotellic learning loop work? Let's go a little bit in more detail, and then even in more detail later on. And so basically, first the agent observes the context and samples the goal with its internal goal generator. Then it generates appropriate actions with its goal condition policy to pursue the goal inside the environment. And after it has taken actions and rolled out a full trajectory, it uses basically its own goal achievement function to evaluate its performances. So sometimes it might succeed to the goal it has set for itself, but sometimes it might fail. But even when it fails, most IMJEP algorithms include some forms of hindsight learning, which are basically a mechanism that is relabeling the achieved trajectory by a posteriori imagining the goal that could have been imagined and have been reached in this particular trajectory. And so actually this means that now you have an example of a successful trajectory for that goal, which enables to update usefully the internal model. But research on autotelly agent poses many challenges to achieve efficiently and autonomously this loop. And so here I would like to illustrate a few aspects of this research. So just also a remark before going into some examples. When I speak here about goals, I really speak about an abstract, generalized notion of goals, which means it's not like I'm not only speaking of goals as, for example, concrete configurations of a scene that the agents may want to achieve, but I'm really discussing about abstract parameterized problems associated to parameterized reward function to score the achievement of those problems. And so goals could be relatively concrete, such as, for example, pushing an object A to a location parameterized by X, Y, Z, and using a simple goal achievement function like the L2 distance in the object Cartesian space. But it could also be something like build something that has an image embedding that is corresponding to a certain vector in a spatial embedding space E. It could also be a combination of an objective with some constraints. So for example, a goal could be move as fast as possible while ensuring the steps are smaller than E, or have a style that is of type T, and the reward might be the speed if the constraints are satisfied, and 0 if the constraints are not satisfied. Could be, for example, to make an acrobatic jump with 2 loops while saying hello, or executing a following a natural language command. So it could be anything that can be parameterized in some space. But now let's begin by examples which are very concrete and where goals will not be so abstract. I will come back to more abstract goals later on. Let me begin by a simple population-based instantiations of IMJEP. So here we imagine a multi-dimensional robotic arm, and we imagine that motor policies are parameterized in a very simple manner, very simplistic manner. So this is just for the matter of explaining the basic ideas. And so basically here, the motor parameters is a set of vectors specifying the target value of the PID controllers of all motors. And then when this is achieved through the unknown dynamics of the robot body and environment, it's going to produce a trajectory of the robot. And then there is we assume here that there is a system for observing features out of this trajectory. And let's assume here we have decided to measure only the final 2D position of the tip of the arm after PID stabilization. And then something that we have now as ingredient of those IMJEP, and then later on I'm going to explain how we are going to use this, is that now we consider a space of goals, and actually the space of goals is actually a space of cost function, the space of reward function, which take as input the features computed from the trajectory and also each parameters of a given cost function, so a given goal. For example, tau here is used actually to compute the achievement of that goal, which is here simply, for example, if tau is the target tip position, simply the distance to the target tip position. But you'll see later, this can be much more abstract than this. Okay, so we have a space of goal, which is basically a space of reward function, parameterized here by a target position. And now, also, when we have the robot exploring, so it's going to progressively collect a memory associating the parameters of the motor policy theta, so the context, the initial context S, and the outcome features of the trajectory W. And then from this data, there are several things one wants to learn. So first of all, we want to learn a predictive model that's predicting basically the features W given the parameters of the policy theta and the starting state. And this can be done using whatever your preferred regression method. And then we want also to acquire a meta policy which is a form of inverse model, which given a goal or given a reward, a parameterized reward function, and an initial context is going to provide the parameters of the policy that will minimize this cost function or maximize the reward depending on the way you see it. And one way to do this is actually to do optimization over the forward model F that you have here, which you can do with whatever is your preferred optimization method. And then based on those tools, the basic population-based loop of the IMJET goes as follows. So first of all, you have a bootstrapping phase in which basically you are going to sample random policies. So basically you observe the state, you sample a random parameter of the policy, you launch the experiment, you observe the outcome feature W, and you simply add theta, the initial state and the observed outcome to your database, and then you initialize the first forward model. Then there is the exploration phase, where now you're going to sample goals and try to reach them. So first of all, in first step, you observe the context, then you sample a reward function or a goal using a certain sampling strategy. I will discuss sampling strategies later on. Then you basically use your current inverse model, for example, optimizing over the forward model. Then you launch the experiment corresponding to the motor policy you found. You observe the rollout of the trajectory, you measure the outcomes, you add that to the database, you update your forward model, and you update also the sampling policy. And then in the end, you can exploit what you've learned by exploiting the forward and inverse model you've been learning. So let's look at the corresponding usefulness of goal exploration, even if it is done completely randomly, as opposed, for example, to random action exploration of the parameters of the policy. So imagine that you have a multi-dimensional arm. Maybe you have here 2 joints, 7 joints, 20 joints, 100 joints. If you do random action exploration, if you don't have too many joints, the difference between action exploration and random goal exploration is not so big. But as you increase the number of dimensions, actually what you do when you do this is that you increase considerably the redundancy of the system and also the non-linearity of the system. And as you see, if you continue doing random exploration, you will actually discover less and less of the possible outcomes that you can do with this particular robotic system. On the other hand, if you do random goal exploration, you sample goals directly in the outcome space, you will see actually a graceful degradation of performances, and you really need to have many, many degrees of freedom until you really begin to be not able to efficiently discover the variety of outcomes. So in a way, doing even random goal exploration is a way to be efficiently discovering the diversity of outcomes that are possible with a given robotic system, such as the one I presented here. However, here I said you can be efficient with random goal exploration on random goal sampling, but still you need to be careful in what is the space in which you sample and how you sample it. Because, for example, if the space in which you sample the goals is smaller than the actual space in which it's possible to reach, then actually you will be suboptimal in discovering the possibilities. And if you increase the size of the hypercube in which you sample goals, you will also begin to be less efficient, as you will actually, in priority, only discover outcomes at the frontier of what's possible, but not so much within the cloud of what's possible. So maybe it means that we need more sophisticated mechanism than random goal sampling, and I will discuss that in a few minutes. But just before going into sophisticated goal sampling mechanisms, I'd like also to illustrate the fact that the loop I described now with a very simple kind of goals can actually consider much more elaborate kinds of goals. For example, this is what we observe when we look at quality diversity algorithms, such as the Metadiversity system, which can actually be formalized as a particular kind of IMJEP. So for example, in the Metadiversity system, you have this robot with multiple legs, and then it has a system of parameterized motor policies with 36-dimensional continuous parameters that control basically parameters of the oscillations of motors. And then it produces trajectories over a few seconds of rollout of the behavior on which features that are measured that are the things like the forward speed, but also step patterns. For example, vectors characterizing portion of the time each leg is in contact with the ground, which is a way to characterize the style of walking, if you want. And then you have a space of goals, a space of reward functions, which are called cells in the mapped systems. And so when you sample a goal, you actually sample a cell, and a cell actually defines an objective consisting of trying to maximize the speed while trying to display a pattern of steps that is respecting certain constraints. And so if you are trying to improve your capability to move fast within this particular style of walking constraints, you can actually improve the local capabilities. And sometimes you try to do this, but you don't manage to improve with this style, but you find another style which improves other cells. And this is what the form of hindsight learning that's observable in that kind of system. And so basically here it means that a goal is something that is the combination of a cost function that might be, for example, interesting for an end user engineer, combined with compliance with some constraints, and the space of constraints is parameterized into a number of cells, and so it's equivalent to have this space of goals. And that's also a way to see how IMJEPs can enable a robot to explore a diversity of skills that are going to be still relevant and useful for a downstream task for an engineer. And this is in particular very useful here, as the authors of this paper were able to show that if you learn to walk fast, not only with one style, but a diverse set of styles, then in case, for example, you have a motor that is broken, then you could probably find a style of walking that does not really use a lot this broken motor and still is very efficient at walking fast. So you can readapt very fast. Okay, but now let's come back to one of the important problems is learning to sample goals in a way that's better than random goal exploration, and how to realize some forms of self-organized learning curriculum. So what's an interesting goal? What's an interesting learning experiment? So there are many ideas that have been proposed in the various literatures, actually ranging from psychology to biology to AI to reinforcement learning, quite often independently. So one example of idea is that an interesting experiment is one which leads the experience of high novelty or high control errors or high prediction errors. But in the real world, it's not going to work at all. So this will lead, for example, a robot to spend its whole day staring through the window, making movements with its arms and trying to predict how the color of cars passing by change as a function of movements. And of course, it's completely stupid. And you will not learn like this. But if you tell the robot explore goals or situation which leads to high prediction or high control errors, it is what it will do. Among other ideas, several of them are interesting, but I will now focus on one that we've been studying a lot, initially inspired by some limits of theoretical ideas of biologists Varela and Maturana, but that has also shown to be very robust to guide robot learning in the real world, as well to account for some developmental phenomena that we observe in human children. And so this idea is that the interestingness of a kind of experiment is proportional to empirical change in goal achievement errors. And so this change can basically be an improvement, but it can also be a decrease in competencies, which will enable to drive interest to parts of an environment that change or to skills that are being forgotten. And so we call this idea the learning progress hypothesis, but actually it includes also learning regress. So such a mechanism can actually self-organize a form of learning curriculum. And so to visualize how it's possible, let's imagine an abstract situation on the top right here, where a robot is confronting with 4 kinds of sensory motor activities, each of them characterized by a different learning rates. As we see on this graph with the different colors, which correspond to different kinds of activities. So each curve basically shows the evolution of the errors in each of those activities if the learner would focus on practicing each of them. But then the exploration driven by the learning progress principle basically will result in avoidance of activities that are too easy or too difficult to learn. So here the blue one and the red one. And first focus on the activity with the fastest learning rate. So here initially the black one, and eventually when it starts to reach a plateau, to switch to the second most promising learning situation, which is here the green one. So let's see here how this kind of goal sampling mechanism based on learning progress, as well as an advanced form of the IMJ loop I presented before, can be instantiated in a more complex real-world robotic experiment. So here we have actually an experiment where a humanoid robot can explore its body and how to interact with many objects. Some of them can actually be used as tools. There are also several distractors in the environment, which means that there are objects that are either too far to be moved or that move autonomously in a random manner. So here the robot is actually able to track the position, the color, and sound of all objects. So we are actually assuming there is already a sophisticated perceptual system that is object-centered and that is already working and given to this robot. In terms of action, so the robot can produce actions that are parameterized here by 32-dimensional dynamic motion primitives, which I guess many of you are familiar with, which are basically dynamical systems with some parameters. Then it has several actually groups of behavioral descriptors that we call modules that are characterizing the trajectories of various objects, as well as the trajectory of sounds and the trajectory of light patterns, both produced by those objects. And so in total, we have actually a descriptor space with 310 dimensions, but they are organized in around 15 modules, which correspond to actually particular objects. And each module has around 20 dimensions. And as actually you see on the right, we've actually a farm of these humanoid robots that has enabled us to make many experiments. Actually, these robots are the open source Poppy platform that are 3D printed and that were also designed by my team and that are now disseminated and further versions have been produced by both a startup company from the team, which is Pollen Robotics, as well as an NGO, educational robotics called Poppy Station. And that's used actually by many universities and schools in the world. But okay, let's come back to the machine learning experiment here. Okay, so now let's look at the system. And just one thing I want to emphasize is, as compared to the system I described before, one important change in this experiment is that goal exploration will be modular, which in the sense that when the agent is going to set a goal, it's going to be setting a target trajectory for only one of the different objects in the environment. So that's not a target configuration. That's not a static configuration. That's more complicated. That is a dynamic trajectory, the goal, but it's not also a dynamic trajectory of the full scene. It's only a dynamic trajectory of part of the scene corresponding to one object. And then the way to sample goals is by actually estimating the learning progress or the competence progress to control the trajectories object by object. And so initially the robot will not know where there is learning progress and will progressively discover and sample the goals where it is providing most learning progress. So initially, actually, he doesn't know where learning progress can be made, so he samples goals for many objects around, but relatively quickly, he will discover that there is one special object for which it makes most learning progress, and that is actually the hand. The hand initially is perceived as one of other objects, but it is nothing special for the robot initially. It becomes special because it's the first object that is providing high learning progress. So here we actually see internally in the head of the robot the learning progress curve for the hand, which is rising. And so by doing this, actually, it is now focusing on setting goal for the hand, which is actually going to lead to discover a higher diversity of movements of the hand, which in turn will lead the robot to discover how to move those two little red things, which are joysticks. And now they become a niche of learning progress, and now he's focusing on moving them. But then actually he discovers that moving one of them actually leads to learning progress in controlling this little white electric toy that you see on the right. Actually, one of the joystick controls these white electric toys. And so now setting goal on the white electric toy becomes also a source of learning progress, and he's focusing on this. And then in turn, he discovers that setting goals on moving the tennis ball here around becomes interesting. And so in a few hours, he moves from not knowing how to explore, to learning to explore the hand and learning the joysticks, then learning how to control the electric toy, and then finally learning how to control the ball. So we learn the whole set of skills, even in the presence of multiple distractors that are in the environment. And some of the skills are non-trivial, such as what you observe right now. And this is done basically between 10 and 15 hours of real time on the physical robot without any simulations. Okay, and so now if we look at the curve, we can also see, interestingly, the efficiency of such approaches. So here the system that is sampling goals with learning progress in a modular manner are the blue curves, and what we show on those different curves is the speed at which the robot is discovering a diversity of skills for controlling various objects. So here you have the hand, the left joystick, right joystick, the white electric toy, and then the ball. And then you have also other sound and light things. So the blue curve, as you can see, is close to the top for most of the curves. And so we have some baselines and an oracle. So among the baseline, we have random policy exploration. This is the green one. The green one is only good for exploring the hand, but starting from the left joystick, it becomes very bad. And it's very, very bad, for example, for discovering how to move the ball. It does not discover at all how to move the ball. Then you have another baseline, which is what we call single goal space. It's like, imagine we would like the robot from the start to learn to move the yellow ball. And so instead of letting him free to explore goals about various objects, we impose this robot that he should only sample goals about moving the yellow ball. So it's basically suppressing most forms of curiosity. And so actually we see that this is actually very, very bad at learning to control the ball and even the ergo robot. So that's very, very bad. And it shows the usefulness of being curious, exploring the whole set of environment, even if you want to solve one specific problem like moving the ball. And then we have an oracle, which is the green curve, which is basically like trying to put by the hand most of the expert knowledge we have about this robotic system to design by hand a curriculum of learning, where we actually start by saying to the robot, first focus on the hand, then on the joystick, then on the electric toy, then on the ball, etc. And actually what we see is that the oracle is pretty good, sometimes even better on the joystick and the ergo robot, but for the ball, actually it's ending up much worse performance than the blue curve, which is using learning progress for sampling goals, and even the orange curve, which is random goal sampling in a modular manner, but without the learning progress, which is less good than using the learning progress, but better than the oracle and orders of magnitude better than the two baselines. Okay, so now this was examples of IMJEP with population-based systems. So here again, remember this was a population-based system in the sense that the robotic system memorized explicitly the history of policy parameters and outcome it reached, and it would use that to train a forward model, which actually was trained in that particular case online, as depending on the goal, you train a local forward model and you repeat that. But it's also possible to build an IMJEP architecture with very standard modern goal condition deep reinforcement learning systems. So this is, for example, something that we've been doing with the Curious algorithm. And so here we are basically starting from a very standard deep RL architecture, which was DDPG, but we could have used the SAC algorithm, for example, also. And the update that we do is that now we are considering what's called UVFA, which means that in addition to the current state in input of the actor and the critic of the neural network of the reinforcement learning system, we add some input neurons which encode the goal. And then updating the UVFA system, because we want to have modular goal exploration, like in the system I just presented. Actually, we have a modular encoding system which enable to encode the fact that sometimes the goals are not about moving all things in the environment, but only part of the. So let's study this idea in the context of the simulated robot we have on the top left here. Here, the robot is free to choose or switch to any goal he might try to learn and achieve. And in this particular experiment, he is given a space of goals to sample from. That's including reaching, grasping, or stacking various objects. So one challenge is that here we put distractors. So for example, there are objects that move randomly and cannot be controlled. But here there are many goals in this goal space that are impossible due to these distractors. For example, stacking uncontrollable object is impossible, but initially the robot does not know. But also even among the feasible goals, some are easy, some are more difficult, and depend on mastering other goals to be learned. So if the robot samples goals randomly, it will be very, very inefficient at learning. And so basically there is a need for automated curriculum learning. And this is really realized by sampling goals according to their expected absolute learning progress. So in practice, there are actually two kinds of difficulties that we need to solve. The first kind is how to estimate, how to track, how to predict learning progress for various kinds of goals. For this, we develop specific regression models. And another kind of technical difficulty is how to find efficiently the niches of learning progress. For this, we've been using bandit algorithms such as the X4 system that are especially made for non-stationary bandit system. And here, if the utility of the bandit is learning progress, this is indeed a non-stationary problem. So today, what I want to focus on is not rather how to solve these technical problems, but rather what are the good properties of these sampling skills when you can estimate well this LP. So on the right, we actually see the emergence of a learning curriculum, where on the top, you see the progressive acquisition of skills of increasing complexity. And on the bottom, you see the estimate of learning progress, which is proportional to the probabilities to select each goal type. And then we can check actually that there are 4 goal types, 4, 6, 7, which are actually the unlearnable ones in this environment. And they are indeed very little sampled. And so basically the system has learned to sample the goals of appropriate complexity, avoiding those that are either too difficult or too easy. And a very good property of this goal sampling scheme is that it can address one particular problem that we have when we use parametric models such as neural network, which is catastrophic forgetting. So catastrophic forgetting happens when sometimes with neural networks, when you train them on new tasks and you don't train them anymore on past tasks, and basically sometimes it erases what was learned about the previous task. And so here we see this phenomenon on the left, when after mastering the green type of goal, the robot focuses on the yellow one, and this actually leads to a drop in performance of the green type of goal. But this is catched by the estimate of absolute learning progress that we see in the middle, as there is actually learning regress. And as we are looking really at the absolute value of the derivative of the learning curve, we can spot that. And then, so the green task is repractice again due to the bandits maximizing the absolute value of the derivative. And then this leads to reacquisition of the task. And at the end, everything ends up being mastered and well memorized by the neural network. So now I'd like to discuss how it's possible to learn those goal representations. So in the examples I discussed so far, it was the engineer who was provided already a representation of a goal space. It could be complicated. For example, in the map-edit example, or if in the modular trajectory example of the humanoid robot I described, it was a complicated goal space, a large goal space. But still the engineer provided that goal space. But then the challenge is how you can learn a goal embedding. For example, when you have robots that are perceiving raw images. So one natural approach has been to train a generative model, such as variational autoencoders, to learn an embedding of images and to sample the goals in that embedding. So this was made, for example, in the RIG system with uniform sampling in the prior, or with UGL or SkewFit, where goals are sampled on the frontier of the known distribution. That's actually implemented a form of novelty search. So the advantage of this is that it enables much more autonomy as compared to the systems before. But yet these systems were not robust to environments with distractors or simply large environments with multiple objects. So one way to address this has been actually to use forms of unsupervised learning of generative models that learn disentangled representation of the environment. So one of the first kind of model that were used in this direction was the beta variational encoders. And basically the idea is that this neural generative model tries to learn a latent space where latent dimension of the embedding correspond to independently controllable features of the environment. So for example, different features of different objects. And while learning this embedding, one thing that is possible is now to use that to do modular goal exploration by sampling only target values of a subset of those learned embedding dimensions, which basically correspond to sampling target transformations of particular objects in the environment. And we can use, again, learning progress in that embedding space to organize also the exploration in a way that is very similar to the humanoid experiment I showed before, except that here the features, object-based features, are learned from images. Okay, so I'm late, so I will be fast, but just to explain that what's interesting is that when you use learning progress to sample goals in that embedding, it's not only useful for efficient exploration, but it's also a way to discover actually which of the embedding dimensions that are learned correspond to learnable objects and which other to uncontrollable objects, which can be very useful. And here, these are curves showing the evolution of the diversity of acquired skills, basically showing that with the learned modular goal embedding I just explained, we can basically reach performances that are very, very similar to hand-defined modular goal spaces, and much better than either using flat goal spaces, even if they are hand-defined or learned, and much, much better than random exploration of the parameters of the policy. Okay, now I'd like to discuss another topic which addresses another limit of the approaches I discussed so far. And I'd like to introduce the concept of metadiversity search, as well as to put back a little bit the user in the loop. So all the approaches to learn a goal embedded I discussed so far basically assume that the intuitive notion of diversity can be captured within a single goal representation space. So this limits the scope of the final discoveries, which might be diverse in the chosen goal embedding, but actually poorly diverse in other potentially interesting ones. So again, if we look at children, it seems intuitively that they represent their goals in different ways, depending whether they aim to build a Kaplan structure or prune a tree in a certain shape, or do a skateboard trick, or even aim to cook a meal of their invention. They don't represent their goals in the same way in those different contexts. And so to address these limits, we've recently formulated the problem of metadiversity search as a problem where an agent incrementally learns a set of diverse goal embedding spaces in an outer loop and searches to discover and achieve diverse goals within each of those goal embeddings in an inner loop using an IMJ. And so we also considered how, with minimal external feedback from a human user, the agent should be able to efficiently specialize the exploration strategy toward the human initially unknown preferences. So to solve this metadiversity search problem, we've been developing an IMJ approach that incrementally learns a hierarchy of diverse goal embeddings. This is something we presented at NeurIPS last year. So the hierarchy starts with a single variational autoencoder. Actually, you could apply the same idea with other kinds of generative models. And this generative model is incrementally trained on the incoming data, encoding it into its latent space. So when the reconstruction loss of the VIE reaches a plateau, a split is triggered and two child networks are instantiated. Then there are lateral connections between the parent and the child VIE, allowing the child VIE to reuse its parent knowledge while learning to characterize novel dissimilar features. And each new observation falls into one of the leaves corresponding to different goal embeddings. And this is updated and split again recursively. So basically, all the leaves form a set of goal embeddings, and goal sampling is made here in a hierarchical manner. First, you sample a goal embedding, and then you sample a goal inside it. So to quickly adapt the search toward the preferences of the external user, then it's possible to ask the user to assign an interest score to the different leaf nodes when there are splits. And this is both simple and relatively rare. So one can prioritize exploration in those models, in those nodes, in the goal sampling strategy. So actually, this work was also the opportunity to explore what I think is a very important and interesting area of application of IMJ algorithm, and which is quite different from traditional robotics. So basically, IMJ can be used as tools to help scientists to make discoveries for complex systems in physics, in biology. And as you'll see in a minute, actually robots still play a role, but it's quite different from what many of you are used. So for example, a previous PhD in my lab, Jonathan Grisou, went to do a postdoc in a chemistry lab in Glasgow. And in this lab, they are studying the origins of life, and they want to understand how certain oil droplets with certain chemical characteristics can self-organize into protocells. And they discover that certain kinds of oil droplets have amazing self-organizing properties, such as what you see on the video right now on the screen. But they have no chemical model of those chemical systems. It's too complicated for existing chemistry and physics, so they cannot do any simulation. And they have very little understanding of what's possible to achieve in that complex system. Until very recently, they were just trying manually with their own intuition to make various kinds of mixes and observing what happens. A few years ago, they began actually to automatize the lab by building a robotic system that is actually being able to do the full experimental loop, mixing the oil droplet as you see on the screen, and then using a camera to measure the self-organizing system. And then what Jonathan Grisou began to do was actually to use the IMJEP system to drive exploration to do better than random goal exploration or grid search exploration. And he was able to show that if you do goal exploration with those systems, you can actually discover a much wider diversity of chemical and physical structure that you can do. And so we began actually to launch a research program on this topic, and we are also using now digital systems like continuous game of life to study them. And then we've been using the representation learning for metadiversity that I just presented before to you, and using that to discover new structures in continuous games of life. We could actually show the discovery of novel structures that people studying cellular automata were not able to find in a systematic manner before. So for example, we were able, so here there was a video, we were able to find some kinds of system generating gliders in those continuous game of life, which was only known in discrete game of life so far. And then we were able actually to show how it's possible to guide the system with very few input from the human. For example, imagine you have a human who wants to have localized patterns like little creatures in those game of life system. We see the evolution of representation and discoveries on the left that's specializing to this. But if you have a user who wants to find Turing-like patterns covering the whole screen, then you have the system discovering, making a different specialization on the right and making different kinds of discoveries. Okay, just in 1 minute, there is a topic I will not have time to discuss, but I'll just mention it for those who want to take that offline. Another branch of work we've been doing, and that's very important in the recent years, is to go to a more abstract kind of goals, which are goals based on using natural language. Like children use a lot language to imagine abstract goals and to simulate imagination. And basically, we've developed a system called Imagine, we presented also last year at NeurIPS, in which basically an agent initially interacts with a social peer that is using language to describe what the curiosity-driven agent is doing in a Minecraft-like environment. And then actually the agent is internalizing the model of language and the model of the social peer in such a way that later on, when it is alone in the world, it can reuse language to imagine goals and to imagine how a goal achievement function for those goals could be. It's like internalizing in the head a model of the social peer when the social peer is not there anymore. And we show that using language powers very efficient creative forms of exploration, enabling the system to make discoveries out of distribution much more efficiently than if, for example, you would use low-level concrete kind of goals like in the system I presented before. Okay, but I will conclude here, and I thank you very much for listening. Thank you.
Thank you. Thank you, Dr. Pierre-Yves. Any questions? I have one question, Dr. Pierre-Yves. So, could robot be a scientist, like a physicist or biologist, to do curiosity-driven research? So what's the goal then?
So the goal, as I said, is to help the human scientists to make discoveries. So, for example, as I said, in the system I was presented here, this is a real chemistry lab with real chemists, and they were really like in front of a major problem. They have a complex system. They want to study to unfold big mysteries of the origins of life, but they have no model of this system. They cannot make any simulation, and this is very costly to make experiments in the real world. But still, they don't know how to organize their exploration and how to map the space of possible structures in this complex system from which they might base building a mathematical or a physical model of what's happening. And so here, basically what we are doing is that we are providing a set of algorithms that actually the physicists can influence or the chemists can influence in various ways. And that's going to help him or help her discover and model much more efficiently the complex system he is trying to discover.
Thank you.
We have a question from the audience here.
Hi, Pierre. Thanks a lot for this great overview. I have a question. So in this intrinsically motivated behavior is, of course, great. We are also working on it, of course. But if you have a big space, then it's very difficult to not just go for completely useless kind of goals, right? So you explained a little bit with the language and so on. So what other types do you see to incorporate usefulness or task behavior into this realm?
Yeah, are you still seeing my screen or not? Maybe not. Okay, whatever. So thank you very much for this question. So indeed, actually, what I didn't have time to explain in the last part of my talk is that actually language is precisely one approach to deal with this problem. Indeed, as you just say, if you let an agent learn its own representation in a way that's not at all influenced by any human, there are so many interesting structures in the world that it could actually go in a direction that may encounter obstacles, because it's like a little scientist. He's discovering the world, and if he's not reusing knowledge of others already exploring a particular path, he may actually go in a direction where he discovers that it's actually blocking, and so time is wasted. And so one way to do much better than this is indeed to leverage cultural knowledge already acquired by others exploring the world. And the way to acquire cultural knowledge is by one very important way is by using language as a way to transport not only a language model, but also a model of relevance. So for example, when a human is describing what a robot is doing when he is exploring through curiosity, the human is not going to describe anything. The human is going to describe only things that are of interest to the human brain, and so things that are relevant to the human brain. And so the language, the rules of grammar, but also the lexicon will actually convey a model of relevance. And then this is exactly this model that's going to be internalized and reused by the system later on to imagine and to generate those goals. And so because it will be influenced by this, it will lead actually the system to explore kinds of goals that have a much higher probability to be of some form of interestingness to the human. And it will actually channel very much the system in a particular way. So I'd say that to me, language is one of the important ways to do this, but that's not the only one. As we saw in my talk about the system for helping scientists to make discoveries, we are actually using a very simple way to have the human in the loop to actually push the system towards exploring certain kinds of patterns as opposed to other kinds of patterns. This is relatively simplistic, but still it can strongly influence the exploration. And that's another way to drive the system.
I think that's probably all the time we have for questions. Yeah.
Yeah, there's an online question. Thank you for the very interesting presentation. So my question is about what would be a general way to quantify the results of intrinsically motivated behavior? As for example, learning improvement depends on the expressiveness power of the model and the coverage of the goal space. Even when using dimensionally reduction like a VAE, it is still hard for vast spaces.
Yeah, so there are several questions. Maybe the main answer would be that when we evaluate those kinds of systems, we never use only one measure. And the reason is that those systems can be actually very useful for various downstream tasks. So for example, one example of a downstream task would be that you want that the discoveries made by the robot lead to an efficient model of the world that can be used for many other purposes. For example, model-based reinforcement learning for solving external tasks. Another kind of downstream task might not be directly to build the model, but for example, for the physicists and the biologists here, you just want to have a map of the different possible outcomes. Another kind of downstream task, for example, in the language case, could be not only to make discoveries, but also to generalize better in language comprehension. So for example, in the language system I mentioned at the end, when the agent is exploring by itself by setting its own goals and trying to achieve them, it's not only a way to improve discoveries and exploring the world, it's also a way to train its own policies to generalize in new situations without the help of the social peer. So basically, it enables the system to generalize better the understanding of language sentences with lower number of feedback from the social peer. And so basically, in that case, for example, one of the measures that we use for evaluating the system is basically how much the train policy generalized on the test set of linguistic commands with various, actually we consider various kinds of test set because there are various kinds of generalizations. So we can use this, we can use those measures of coverage when of the space when what's interesting is the diversity of discovered outcomes. We can measure different cost function about the learned world models. So we always use basically a battery of tests rather than a single test because those systems can be useful for a diversity of downstream tasks.
Okay, let's finish the question. Let's thank Dr. Pierre-Yves again for this exciting tutorial. Thank you very much, and thanks for everyone. And